Hello everyone. Today I'm going to talk to you about a remarkable figure in the history of mathematics and astronomy, Battani. While his name might not be as widely known as some other historical scientists, his work was absolutely groundbreaking and laid the foundation for much of what we know in these fields today. Battani was born in 858 CE in Haran, which is in modern-day Turkey. This was a city that was known for its blend of cultures and intellectual life. It was a place where knowledge from Greek, Indian, and Persian traditions converged, and it's where al-Battani began his education. In his day, Haran was part of the Islamic Golden Age, a time when scholars were making huge strides in mathematics, science, and philosophy. Al-Battani had a deep interest in astronomy, and this would become the focus of much of his work. His observations of the cosmos weren't just good, they were precise. One of his major achievements was improving the measurement of the solar year. Based on his careful calculations, Al-Battani determined that the length of the year was 365 days, 5 hours, 46 minutes, and 24 seconds. If that sounds familiar, it's because it's incredibly close to the modern value of 365.24 days, which shows just how accurate his work was. But al-Battani didn't stop at the solar year. He also worked on refining our understanding of the moon and the planets. His observations allowed him to calculate the tilt of the Earth's axis more accurately than anyone before him, and he made corrections to the astronomical tables used at his time. His work improved the understanding of how celestial bodies moved across the sky and helped future astronomers make more precise predictions. His influence spread both across the Islamic world and later into Europe. These astronomical discoveries would not have been possible without extensive knowledge in mathematics. When it comes to math, al-Battani's contributions were just as revolutionary. One of the areas where he made a lasting impact was trigonometry. You see, before al-Battani, trigonometry was largely based on chords in a circle, which was used by earlier Greek astronomers like Hipparchus and Ptolemy. But al-Battani took this idea and pushed it further, laying the groundwork for modern trigonometry as we know it today. He was among the first to systematically use the sine function, which was a refinement of the chord function. By focusing on sine and its properties, al-Battani was able to calculate values with much greater precision than his predecessors. This was especially important for astronomical calculations, like determining the positions of the stars and planets. He also compiled accurate trigonometric tables, which were essential for future astronomers. His tables included the values for sines and tangents of various angles, which helped astronomers measure and predict movements of the celestial bodies. On this slide, I listed two trig equations that he produced, and then also wanted to show that he solved this equation, which in turn helped him to discover the equation below that. This picture on the right is something that I found that was his method of figuring out these trigonometric functions, but it's a little more complicated than I know how to explain, but I thought I'd include it just because I thought it looked kind of cool. One of the most significant innovations that al-Battani made was his work with spherical trigonometry. Spherical trigonometry deals with the relationship between angles and sides of spherical triangles, shapes that are fundamental to astronomy. These triangles appear when you map the stars and planets onto a celestial sphere, and understanding them is crucial for calculating things like the positions of the sun, moon, and stars. Al-Battani developed several important identities and formulas that helped future astronomers and mathematicians solve problems related to spherical trigonometry. For example, one of his key contributions was the refinement of Ptolemy's theorem for spherical triangles. Specifically, he corrected some of Ptolemy's tables for the positions of the planets and developed his own methods for predicting the methods of celestial bodies using spherical trigonometric formulas. This allowed for more accurate calculations of planetary motion. He also helped to define the laws of sine, cosine, and tangent for spherical triangles. Finally, he worked on improving the calculation of angular distances between the stars, and his work on eclipses became a cornerstone for later astronomers. This work on spherical trigonometry and astronomical tables was pivotal in advancing the science of navigation. By calculating the position of celestial bodies accurately, sailors could navigate the seas with much more precision. This was incredibly important in the centuries that followed, particularly during the Age of Exploration. What's incredible is that al-Battani's work didn't just fade away after his death in 929 CE. His ideas continue to shape the development of science, particularly during the Renaissance. Scholars like Copernicus used his tables to refine their own theories about the motion of the planets. In fact, many of his astronomical models we take for granted today are built upon the work of al-Battani and others from the Islamic Golden Age. His most famous work, Kitab al-Zij, the Book of Astronomical Tables, was filled with his detailed data and calculations, including his correction to earlier models of the solar system. This book was widely circulated across both the Islamic world and Europe, where it influenced mathematicians and astronomers for centuries. As we have discussed in class, the development of mathematics is really only possible when many cultures are exchanging diverse ideas. Al-Battani's story highlights the power of this cross-cultural exchange. He was part of a tradition of scholars who drew upon the knowledge of ancient civilizations and built upon it, making important contributions to scientific knowledge of their time. His legacy reminds us that scientific progress is rarely the result of isolated effort. It is the result of long, interconnected history of learning, discovery, and innovation. In closing, al-Battani's story is a powerful example of the incredible potential for human achievement. His ability to blend mathematical precision with astronomical observation and his willingness to refine the work of his predecessors set him apart as a true pioneer. His work didn't just shape his own time, it influenced generations of scientists to come, and his contributions are still relevant to us today. Thank you for listening, and I hope this speech has been informative.